Research here at the University of Latvia, and it is my pleasure to welcome you here for a very special event. And it's welcoming Professor Robert Tarjan here today. As the James McDonnell Distinguished University Professor at Computer Science at Princeton University, he's a true legend in the field of algorithm design and data structures. And his pioneering work in many places has shaped the field tremendously. His contributions from the union-defined algorithm, Fibonacci heaps, splay trees, and many others are at the foundations of computer science. And this is visible in simply checking the number of citations other people have cited his work. It reaches more than 100,000, so it's indeed something you don't see that often. And it indeed reflects the influence that you, Professor, have put to the field, and indeed this is a great privilege of us to welcome you here. And this impact has been recognized also by awarding the Turing Award in 1986 for this work. And I think no computer scientist, and here we have plenty of aspiring ones, have gotten far without running into Robert Tarjan's name at least several times, and I hope you can convince this, and afterwards in questions and discussions go for this. And what's great that Professor has by no means stepped away from research or teaching, and he remains fully active, as we will see here today as well. And just last year he was co-authoring a paper titled Universal Optimality of Data via Beyond Worst Case Heaps, for which he received the Best Paper Award at IEEE Symposium on Foundations of Computer Science. So be active for long term, and this gives you results. And you can he also gave a talk on this topic, which you can find in YouTube. So by entering Tarjan and Dijkstra. So go for it after this lecture. Before I give the floor to Professor, I have to say thanks also to others, and that's mainly the University of Latvia Foundation, and especially entrepreneur Wolf Adam for supporting this event in many ways. And I'm very glad that Wolf is also a PhD student at our university. But now please help me with applause to welcome Professor for his talk that you can see here, My Life with Data Structures. Thank you again.
Thank you. It's a great treat to be here. This is the fourth or maybe the fifth time I've been in Riga, and every time I'm here, I enjoy it even more. My life has been a wonderful experience. I kind of think of myself as Forrest Gump, you know. He was in the right place at the right time, and I was kind of in the right place at the right time. I have to thank all my brilliant students, colleagues. I love working with other people, and what I'm going to talk to you about wouldn't have been possible without their contributions. And I also want to acknowledge my wife, our 5 children, and our 6 grandchildren who make life meaningful beyond data structures. So this is a kind of a double origin story. I want to describe how I got involved in the work that I've been doing for a very long time. And also how some of these concepts arose. They didn't come out of thin air. It took many years to develop some of these ideas. So when I was in elementary school, I loved science fiction. I wanted to be the first person on Mars. Actually, that's still achievable, but that's no longer my ambition. Then 7th grade, roughly, I started reading a column in the Scientific American by Martin Gardner called Mathematical Games, and I got intrigued by mathematical puzzles and games and so on. And then I had an amazing math teacher. This was in public school in Southern California, who taught us Peano's axioms. This was the new math before there was any new math. And we were doing proofs by induction in early junior high school. There were no computers at that point. So I got really interested in mathematics, went to Caltech as an undergraduate, majored in mathematics, got interested in the 4-color problem, And you may know that eventually, so what is the four-color problem? Given a planar graph, color its faces with four colors. Prove that this is always possible, so that no two faces sharing a boundary have the same color. So if you want the color maps to distinguish countries, you need an algorithm to do this. Of course, some countries are not all in one piece, which complicates things. In any case, there's a beautiful proof of this that I think is more in the computer science vein than in the mathematics vein, which uses an induction with a complicated case analysis. And the case analysis is pretty much too hard to do by hand. It has to be done by a computer. And this was very controversial at the time among mathematicians, but I think it's more and more accepted today. There are certainly theorems that one needs a mathematical theorems that you need a computer to assist with the details of the proof. So planar graphs, here's an algorithmic problem that actually got me started in research, which is the problem of planarity testing. So I was at Caltech as a mathematics major. There was a question when I got my degree, my bachelor degree, whether to go into computer science or mathematics. I applied both to a PhD program in math and PhD programs in computer science. Ended up going to Stanford in the computer science department, hoping that I could do mathematics that would be applicable. And I had some experience with implementations on very primitive machines. The first machine I ever programmed on was called a Bendix G15. It was a refrigerator-sized box. The input was paper tape. We programmed in assembly language. It had 2,000 words of memory. It was an amazing challenge. So I got to Stanford. I took a Lisp programming course from John McCarthy, who was also a Turing Award winner, who is no longer with us, unfortunately. But as the final project, he proposed the question, so the project was to implement some interesting algorithm in Lisp. Which, if you don't know, is a symbolic programming language that is very nice for certain tasks, manipulating lists and so on. He proposed as one of these problems, testing the planarity of a graph. So what does that mean? We have a graph, it's a collection of vertices, points, and edges which connect the points. We would like to be able to draw it in the plane in such a way that no edges cross. One possible application is in circuit layout. If you're laying out a circuit and you need to connect certain points, if you have crossing edges, then of course you have short circuits. So there's a beautiful mathematical characterization of planarity, which is due to Kuratowski from the 1930s, which states that if a graph is planar, it does not contain one of these two graphs as a generalized subgraph. So this one is the K5, which is a graph on 5 vertices. There's no way to draw it in the plane without two edges crossing. This one is the K33, 2 sets of vertices with all possible connections, complete bipartite graph on 2 sets of 3 vertices. Now the theorem says that a graph is planar if and only if it does not contain one of these, but the paths, the edges here do not have to be just single edges. They can be arbitrary paths. So if one wants to use this, even though it's a beautiful mathematical characterization, to try to use it as an algorithm, you have to at least look at all possible sets of 5 vertices and all possible sets of 6 vertices, and then you have to find the paths that don't overlap. So this is an expensive computation at best. All the people who tried it in McCarthy's class didn't manage to get a working implementation. But I poked around in the literature and I found this paper, Lempel, Evan, and Cedarbaum, published in 1967. So I was a grad student from 1969 to 1972 at Stanford. And this algorithm actually runs fast. The idea is to actually try to draw the graph in the plane, add a vertex at a time in a certain specified order, and maintain a data structure to keep track of all possible embeddings. Every time a vertex is added, you need to update the data structure to adapt to reduce the number of possible embeddings. They used symbol manipulation and represented their data structure by essentially an algebraic expression, and they didn't worry too much about the details of the implementation. But it turns out that if you're careful about it, there's a way to implement the algorithm to get it to run in quadratic time and the number of vertices. And I did this for my final project in Hartley's course and managed to survive. And then after my first year at Stanford, John Hopcroft came to Stanford. He was professor at Cornell. He came as a visiting sabbatical. And we shared an office together, and we started talking about graph algorithms and techniques for devising graph algorithms. And in particular, the possibilities of using depth-first search to do various kinds of computation. So depth-first search is the ancient technique of essentially maze traversal. You walk through a maze, you always go forward until you reach a dead end, and then you back up and go in a different direction. This is what Theseus used to go kill the Minotaur in the maze and managed to escape because he unwound a thread and followed it back to the entrance to the maze. So here's an undirected graph. A depth-first search might start from, well, let's see on the next slide here. We can start from vertex A and then walk to C, and then we keep going. We go to G, we then back up. We can go to another vertex, D, and then from D to H, from H to I, and so on and so forth. What kind of structure does this impose on the graph? That's the question that we asked. So first of all, we're walking along every edge in both directions, first advancing along it and later backing up. So if we walk along an edge, for example, from C to G, which is a dead end, we immediately back up. But when we start out here from A, we go to C, and we wander around the entire graph, and the last step is actually to back up on this CA edge. So the search imposes a direction on every edge, which is the direction in which we first traverse the edge. Furthermore, it decomposes the edges into two kinds, tree edges and non-tree edges. I've indicated the tree edges in black here. These are the edges by which we first reach a vertex. So we go from A to C, from C to G, back up, go from C to D, D to H, H to I, and so on. The black edges are the edges by which we first reach every vertex, and they form a rooted tree, rooted at the start vertex A. And then there are the non-tree edges, which I've indicated in red here. And the important thing for our purposes that we get out of depth-first search is that every non-tree edge leads from a vertex in the tree to something that is an ancestor of that vertex in the tree. That is, it forms a cycle in the tree. So for example, this edge from K to D, there's a tree path from H to I to K. So there's actually a cycle here that is formed by this KH edge, and similarly for all the other red edges. So what good is this? Well, this allows us, among other things, to compute what are called the bikinetic components or blocks of an undirected graph. These are the sets of vertices that are, it's actually a partition of the edges such that two edges are in the same block of the partition, if and only if they are on a common cycle. So I've circled in blue here the blocks. The blocks are separated by cut vertices or separation vertices. For example, if we remove C, we essentially break the CG component, which consists of just a single edge here, CG, from this component. And H here is a separation vertex, which breaks these two components off from the rest of the graph. And this vertex I breaks the top component here from 2 components off to the right and 3 components off to the left. We would like to compute these blocks fast. And depth first search is exactly the right tool to do this. I won't go through the details, but if you run a depth first search, you maintain the appropriate information, some of which you store in a stack. You can compute these components in linear time, in time proportional to the size of the graph. Now, we took the same idea and applied it to planarity testing. And we applied this to a different algorithm besides the Lamp-Levin and Cederbaum algorithm, which I'll come back to, which is an algorithm that I'll call path insertion, which was invented by Auslander and Parter, who had a mistake, but it was corrected by Goldstein. Goldstein's implementation was something like cubic in the number of vertices, but our goal was to get something as close to linear as possible. So let me describe at a high level the idea here. We can characterize the plane by the Jordan curve theorem. The Jordan curve theorem, another famous classical mathematical result, says that if you draw any simple closed curve, here's a very simple closed curve, this chops the plane into the 2 connected regions, the inside and the outside. This means that if you have any path whose ends are on the curve and do not otherwise intersect the curve, there are only 2 places to put this curve. The path has to be either completely inside, indicated by the red here, or completely outside, indicated by the blue. All right, so the idea of the algorithm is going to be find an initial cycle as a starting point, then find successive paths, add the paths one at a time, and keep track of the possibilities. Now, when we have several paths, all with ends on the same curve, there are essentially 2 possibilities, but they multiply depending upon how many curves we have. So the red curves here, the red paths, I've drawn them both on the inside, but their ends do not overlap. We can put either one on the outside independently of where we put the other one on the outside. On the other hand, for the red one and the blue one here, these have to be on opposite sides. If one is on the inside, then the other one has to be on the opposite side, which we can detect because the order of the endpoints around the boundary of the curve alternates. Here it alternates 1, 2, 3, 4. With these curves, it doesn't alternate. So this led us to eventually build a linear time planarity testing algorithm that combines depth first search. We use depth first search to decompose the graph into the paths that we're going to embed. And we apply this idea to the existing algorithm and maintain a data structure that represents all possible embeddings. Turns out to be a composite version of a stack. It's actually a stack, each element of which is a pair of stacks. And the pair of stacks corresponds to, on one side, there's a set of paths that are going to be on the inside of the curve. On the other side, our set of paths are going to be on the outside of the curve. We can switch them all, but everything has to be switched at the same time. So if we add a new path, what happens to the data structure is that these independently swinging substacks get glued together. But it's possible to keep track of all of this and get the whole thing to run in linear time, which is what we did, and this was the main content of my PhD thesis. At that point, I was programming in Algol W, which was the Stanford version of Algol, which is a lovely high-level language, much better than assembly language. But in those days, everything was on punch cards. My algorithm was a whole box, 2,000 lines of code, and a cardboard box full of punch cards. The way it worked was you punch all your cards, take it to the computer center, give it to them, they run it overnight, get back a printout with 100 error messages, and then you have to correct things. There was a high bar for correctness, and we were very careful in our implementations. Now it turns out that this other algorithm, the one algorithm, the secret-bound algorithm, can also be made to run in linear time because of two results. First of all, you need to determine the right order of addition of the vertices. This is something that they called an ST order. And this, too, can be computed using depth-first search, as Shimon, Evan, and I later discovered. And the data structure, what they had as a simple manipulation problem, there's actually a kind of a tree that one can use to represent the symbolic expression. It's got two kinds of nodes in it, P nodes and Q nodes. And two graduate students independently figured out the right data structure and how to do the implementation to make this whole thing run in linear time. That was Booth and Lindbergh independently. Kelly Booth was a grad student at Berkeley, and George Luger, I think, was at North Carolina. So two rather different algorithms for planarity testing, both running in linear time, and people were kind of surprised that it was possible to solve such a complicated problem in linear time, which is the best possible because you have to look at the entire graph. So what are the high-level points here? Graph algorithms are interesting. Data structures are very useful. Many problems, and we'll see some more examples of graph algorithms. If you figure out exactly what the right information is that you want to keep track of and the operations that you need to do on it, that becomes a data structure problem. Also, we were ignoring constant factors. So back in the early days of algorithm analysis, there were the experimentalists who ran programs and drew graphs and drew conclusions about running time based upon experiments, which wasn't satisfactory to me with mathematical training. And then there were people like Knuth who were counting machine language instructions, getting the constant factors and even getting the lower order terms, and that seemed a little bit too detailed and not transferable from one machine to another or from one programming language to another. So Hopcroft and I adopted the idea of measuring the running time in terms of instructions or operations, primitive operations, but ignoring constant factors. And this turns out to have been a crucial idea in developing efficient algorithms and ignoring irrelevant details. Okay, I got my PhD from Stanford. I followed John Hopcroft back to Cornell. That was my first job. I grew up in Southern California where it's very sunny. I was in the Bay Area at Stanford. I had a fire engine red Mustang, rear wheel drive. I drove from Los Angeles to Ithaca, New York in January. It's snowing in Ithaca. I'm sliding around in the snow. I was not happy about this. I lasted for 2 years at Cornell, and then I retreated back to California, to Berkeley. The last day I was in Ithaca, it was in May. It was a year and a half later. I'm driving out of town. Beautiful spring snow, giant flakes is falling. I took that as a omen to get out of town. Nothing against Ithaca, nothing against Cornell. And the weather is much nicer now because of global warming. But I'm kind of a California person. Now let me describe the next interesting data structure, which is for an even simpler problem than planarity testing or finding biconnected components, but it's related because it's a graph problem. This is the disjoint set union problem, which is a data structure for, among other things, maintaining the connected components of an undirected graph. So we're given an undirected graph. We'd like to find its connected components And we like to allow the graph to change over time. In particular, we want to keep track of components as edges are added. So think of the Facebook friendship graph. Once a friend, always a friend. So you add a new edge and you connect it to a whole bunch of new people, and the edges are bidirectional. How many connected components? Audience participation. 1, 3, thank you. How many connected components? 3, doing well. How many connected components? I think there are 3, but it's not so obvious. How many connected components? We want a computer to do this task for us efficiently and rapidly, and especially in the presence of adding edges. So if the graph is fixed, we can just run graph search every time we start from a new vertex. We reach as many vertices as we can. That gives us one component, and we start from another unvisited vertex, build another component, and so on and so forth. This doesn't work so well if we're adding edges over time. So this disjoint set union, or the union find problem, is a data structure version of maintaining connected components in the presence of edge additions. A little bit abstracted. So the problem is we want to maintain a collection of disjoint sets, a partition, of a set of elements or vertices, and we'll give each set a distinguished element, which I'll call its leader. And we'll want to do 2 operations on these sets. The first one is a find operation, which returns the leader of the set containing a given element. And the second one is put 2 sets together. So we have 2 elements, V and W. If they're in different sets, we want to unite them into a new set. And we'll let the algorithm choose the leader of the new set. So it's easy then to do incremental connected components. We start out with all the vertices in separate sets. To add an edge, we just unite the ends. We determine if 2 vertices are in the same connected component. We find each and see if we get the same leader. Now there's a beautiful, very simple data structure for solving this problem. I'll call it the compressed tree data structure. We represent each set by a rooted tree whose nodes are the elements of the set. Each node has a pointer to its parent in the tree. The root node points to itself, so the root is the leader of the set. We can do our find operation just by following parent pointers to the root, the self-referential node, and returning that node. If we want to do a unite operation, we do finds on the 2 ends. If we get back 2 different leaders, then we make one of them point to the other. If we get back the same leader, we know the 2 elements are in the same set, we don't do it. So very simple. The expensive part is the finds, because when we do these links, over time we can create long paths. And it's easy to build a long path of all the nodes if we don't do anything more clever, and then the finds in the worst case take linear time, which would be quadratic time, which is not so good if we're dealing with a huge example. So we're going to modify the algorithm or improve the algorithm by exploiting the flexibility in the design space here. So what is the flexibility? When we're doing a link, we have the choice. If we have 2 roots, we can make one point to the other one or the other way around. And the other freedom we have is that the tree structure is completely irrelevant. The data structure gets to choose the roots, the leaders. And it doesn't care what the tree structure is, as long as everybody eventually has a path to the leader of the root of the right tree. So to do the linking, we'll do something that I'll call linking by rank, which is a improvement over the original heuristic, which was linking by size. The idea is to always link the shallower tree to the deeper tree. That is, you want to minimize the maximum path length. So we'll give each singleton node initially a rank of 0, and every time we do a link, we'll make the smaller rank node point to the larger rank node. So the ranks are always increasing. In the case of a tie, we increase the rank of one of the two nodes by 1, and then make the smaller one point to the larger one. The effect of this is to reduce the worst case maximum path length from linear to logarithmic. So we get an exponential speed up, actually. This reduces the worst case per find down to log n, which is a whole lot closer to constant than to linear. So this is a good improvement all by itself. But there's even a more amazing improvement, which is path compression, which is orthogonal from this linking strategy, and we do it when we do finds. The idea is run up a long path. We get the answer for all the nodes on the find path. Why not keep track of that? When you walk up a path to get to the root and do a find, we're going to make all nodes on the path point to the root, as illustrated here. So if I do a find on node 1, I'm going to walk 1, 2, 5, 8, 10, and that gives me the answer. 10 is the root, points to itself. I will walk up the path a second time and make all of these nodes point directly to 10. This is compression. Now, if it happens that I immediately do a find on 1, 2, 5, or 8, all of a sudden it's only one step away from the root, so the find is constant time, whereas it was expensive previously. And the only way to increase the time to do a find on any of these nodes is for 10 to become a root of, to become a child of some other node. So there's a competition or a trade-off between the find time and the number of links that happen. And now things get complicated. The algorithm is very simple. But the question is, how does it behave over time? How efficient is this data structure? What's the total time? Now, we don't care too much about the individual time of an operation. The worst case time of an operation is still now log n. A find can take log n time. But this doesn't seem to happen over and over again. And the question is, what happens if you do m, total number of m finds and unites on sets containing a total of n elements? The conjecture was that this would be linear time. Nobody had a counterexample. Knuth posed this as an open problem, basically to prove this result here. This is an example of a simple data structure whose analysis ended up being rather complicated, and the answer to this question is quite surprising. I will give you the history here. Shortly after Knuth posed the problem, there was an incorrect proof of constant time per find. So this is order m plus n times whatever the value is here. This is the time per find in this amortized sense. So constant time, but not a correct proof. Mike Fisher subsequently proved a log upper bound. So this gives a logarithmic improvement over just what you get from linking by rank, but that's not actually tight. The next step was Hopcroft and Ullman proved a log star bound. The log star function is the iterated logarithm, which is the number of times you apply the log to something to get down to a constant. For all practical purposes, this is something like 5 or 6, tiny. But nobody had a lower bound. Turns out the correct answer is that the running time is almost constant, but not quite. This inverse Ackermann function, I'll define Ackermann's function in a moment. I proved the lower bound So the process here was Hopcroft, there was this history of results, and the question was, is it constant or is it not? Let's ask the question, what if it's not? What if the answer is not constant? How do we build a counterexample? So I attempted to construct a counterexample and was able to show that for any k, you can build an example where you can essentially do a find on every element across k long steps. The construction is a double recurrence that pops out with this bizarre function that's on the next slide. But once this idea came into my head, it wasn't too hard to do it, but the hard part was actually proving that that was the answer. But this proves that it's not constant. So somewhere between log star and whatever the inverse of this crazy function is. So being an optimist, I tried to prove the upper bound. I moved to Berkeley from Cornell because I had a hard time with the winters. And 2 years later, I managed to prove the upper bound. This wasn't the end of the story. There was at least one incorrect lower bound proof. And in 2005, Seidel and Shamir came up with another rather different proof of the upper bound, which more resembles the lower bound construction. In any case, what is this function? So Ackermann's function was invented by Ackermann to show that not all general recursive functions are primitive. So we're computer scientists. We all know about the Turing machine. Turing machine was invented by Alan Turing in 1930-something as a model of computation. The question is, what is an algorithm? We need a formal definition of an algorithm. Turing machine is one formal definition of an algorithm, but there are others. The mathematicians came up with this notion of general recursive functions, and the question is, do you need multiple variables to get all possible recursive functions? And Ackermann proved that the answer is indeed yes, by constructing this function that essentially diagonalizes over primitive recursive functions. And you can think of it as a generalized exponential. I won't go through the details of the definition. This is a definition due to Pater and Robinson. There are various alternatives, and whichever one you pick doesn't really matter. But with this definition, there are two variables here, the subscript and the variable in parentheses. And you can think of this as a family of functions, A0, A1, A2, and so on. A0 is just add 1. A1 turns out to be add 2. And then things get a little interesting. A2 is 2n plus 3. A3 is 2 to the n. It's bigger than 2 to the n, actually. A4 grows like 2 to the 2 to the 2 to the 2 n times. And then A5 is even more rapidly growing, and so on. And this alpha function, this is the inverse function. So the A function grows incredibly fast, especially with the subscript variable here, k. And the inverse function grows incredibly slowly. For all practical purposes, it's like 3 or 4. The fact that this algorithm has this bizarre bound, I think this is a wonderful miracle of mathematics somehow. Simple processes, when repeated, have complicated behavior. Think of fractals. There's another thing going on here, which is we don't care about the worst case behavior as much as we care about the behavior of a sequence of operations. So while I was at Stanford, where were we? We were in Berkeley. I went to Stanford, back to Stanford as an assistant professor, and later went to Bell Labs, and here's a little bit of what I did then. The theme here is looking at data structures and applications of data structures in graph algorithms. So I started working with Danny Slater, who was a brilliant PhD student at Stanford, and he followed me to Bell Labs, and we looked at the maximum flow problem. Classic problem. We want to, now we're in a directed graph. We have a directed graph with a distinguished start vertex, a distinguished source vertex S, distinguished sink vertex T. We're trying to send material from S to T. Every arc has a non-negative capacity, and we want to send as much material as we can from S to T, respecting the capacities, so we can't send more flow through an arc than its capacity. And without creating material or destroying material at the intermediate vertices. Here's a very simple example. I've got a source vertex S, a sink vertex T. I can send 100 units of flow from S to A, or from A to T, or from S to B, or from B to T. And I can send 1 unit of flow from A to B. So the black numbers here are the capacities, and I illustrated a flow. This is a flow of 100 units total to T, consisting of 50 units going through A and 50 units going through B. The requirement is that the flow on an edge can't exceed the capacity, and the total flow into a vertex equals the total flow out, except for S and T. There's no point in sending flow into S, and there's no point in sending flow out of T. Now, the classic algorithm for this problem is an incremental improvement algorithm due to Ford and Fulkerson, which is almost a special case of the simplex algorithm for linear programming. They wrote a beautiful book in 1962 on this algorithm and many applications. The algorithm finds an augmenting path, which is just a path from S to T on which we can send additional flow. We send as much flow as possible through the path, and we repeat until we can't send any more flow on any augmenting path. That gives us a local maximum, and the claim, the theorem, the max flow min cut theorem, states that when this algorithm stops, you have a globally maximum flow. Now, critical to this algorithm is the ability to reroute flow. That is, once we've sent some flow, it's possible to increase the flow in a different direction by reducing the flow on an arc. So we have to allow the possibility of sending flow forward, more flow on an arc, or if we've already sent flow on an arc, we've got to be able to reduce the flow on the arc to reroute that flow. Now, all Ford and Fulkerson said in terms of efficiency was if you've got integer capacities, every augmentation is going to add 1 unit to the flow that gets to the sink. So after some finite number of iterations, you're done. But if you're not careful in choosing the augmenting paths, it's not so efficient. And this toy example illustrates the point. So the best way to send the flow, if we're looking at the augmenting path method, is just to send 100 units S to A to T and 100 units S to B to T. We're up to 200. That's the most we can get to T because we've used up all the capacity into T. On the other hand, there's an augmenting path that goes S to A to B to T because of this actually useless edge in the middle. And the bottleneck on this path is this edge in the middle here from A to B. This only allows us to send 1 unit on this path. And if we do that, then we've still got 2 good high capacity augmentations here. We could send 99 units from S to A to T, or 99 units from S to B to T. But there's another augmenting path that goes S to B back to A to T because we're allowed to reduce the flow on this AB edge, which in effect moves flow from B to A. If we send the flow then from S to B to A to T, the bottleneck is this annoying edge in the middle, and we can only send 1 unit. And now we're up to 2 units of flow at T, and after 198 more augmentations, we're done, and if that's not bad enough, let's make 100 into 1,000,000 or 1,000,000,000. And you can construct examples with irrational numbers where this algorithm doesn't even converge to the correct answer and never terminates. So the moral of the story is if you want an efficient version of this algorithm, you need to choose the augmenting paths carefully. So Ford and Fulkerson were working in the days before anybody was thinking about theoretical efficiency. In the late 60s, people were thinking about these ideas, and Edmonds and Clark, who were working in the US, and Dinitz, who was working in the Soviet Union, independently observed that if you always augment along a path with fewest arcs, you get a bound on the number of augmentations that does not depend on the number sizes. It's polynomial in the graph size. Specifically, it's at most vertices times arcs, vertices times edges. So in terms of vertices, this would be cubic, roughly. So is that the end of the story? Not necessarily, because this is the only thing Edmonds and Clark cared about, and Dinitz cared about a little bit more. He invented a data structure to keep track a little bit of reusing information. So what are we losing here? When you send flow along a path, you use up the capacity of maybe one arc on the path. Then the path along which you sent flow breaks up into two pieces. And you know something about those paths. You can still send more flow along those paths conceivably. So why not try to keep track of those paths? And it's not just paths, because so here's a path from S to T. I send flow along it, I break it at a certain point because I use up all the capacity on that edge. I get this path, I get this path. Maybe I find some other path that runs into this path somewhere in the middle. Now this path breaks, and now all of a sudden I get two paths intersecting. I end up, the structure after I've done this for a while is a collection of rooted trees. So we end up with a data structure problem. How are we going to reuse the previous work? How we turned our graph problem into a data structure problem. We need to maintain a collection of rooted trees and send flow along paths in these trees. Now this is more complicated than just finding the root of the tree, but we can define exactly what we need and then look at efficient implementations of a data structure to do what we need. So we need operations of the following sorts. We have a collection of rooted trees, and they're changing over time. We can link two trees together by having an arc from the root of one to a vertex in another. That would tie two trees together. We can also cut a link, which is what happens when we saturate, when we use up all the capacity of an arc. So those are the two operations that change the tree structure. We have to be able to find the root of a given a vertex, find the root of the tree containing it. We've got to be able to find the minimum capacity of an arc along the path from a vertex to the root of this tree. We need to be able to send flow along that path, add the same amount of flow to every arc on the tree. So we end up with something like 5 operations that we have to implement. And this looks like a complicated problem, but there are existing data structures that kind of partially solve it. In particular, we can break up our trees into paths, vertex-destroyed paths. And we can represent each path by a binary search tree. On binary search trees, we can do things in logarithmic time. So the key here is we want to send flow along a long path. It could have lots of vertices. We want to do it all at once. We can't do it in constant time here, but it turns out we can do it in logarithmic time through this data search. So we're representing these paths by binary search trees. And then we have to do operations that rearrange the paths, which I'll call splice operations. So this was kind of in a paper by Galil and Ahmad, and they ended up with a bound which was log squared times. So there's an overhead of log n for each of these binary tree operations. And then changing the path decomposition requires logarithmic time per splice, and they ended up with a log squared bound here. Now the bounds are maybe not so important, but what's important is the idea that is going to come out of this. And here's a picture from an online book by Jeff Erickson that kind of illustrates the decomposition. So here's a tree, and the root is at the top, and it's decomposed into paths, which are the red edges here. And the non-path edges are the black ones. And we represent this tree. So in particular, there's a long path in here that goes from T to Q to L to I to D. We're going to represent this path. This is the actual data structure, which is a representation in the computer of this tree, which is the one we're trying to do the operations on. We make this path into a binary tree, which is circled in red over here. So the operations are on this data structure, and the idea is that this thing is representing a more balanced tree, and if we do things carefully, then we get this log squared bound. But there's no reason to believe you can't get down to log time. And actually, that's what Danny and I did. We managed to combine the two different kinds of operations, do the right kind of path decomposition. You can do it all in the worst case. You can make all these operations on these complicated trees, each one work in log time in the worst case. But it's painful. The resulting data structure is kind of ugly. So what is the alternative? The alternative is to give up on the worst case. As in the incremental set union problem, we don't care about individual operations. We just want the max flow at the end. So we can have expensive operations if they don't happen too frequently. So what do we have to do here if we want this kind of non-worst case behavior? This led us to this idea that was already implicit in the disjoint set union analysis of amortization. And we're doing a sequence of operations, which is always what we're doing on a data structure. Often we don't care about the cost of individual operations. We want to minimize the total cost of the sequence. So we can afford expensive operations if there are enough cheap ones. This gives us flexibility. This expands the design space, and we're trying to design a data structure, an algorithm. This is a big word which comes from the Latin. So amortize means to liquidate a debt by installment payments. It comes from the Latin to reduce to the point of death. We adopted it to analysis of algorithms to mean paying for the total cost of a sequence of operations by charging each operation an equal or appropriate amount. So this takes us beyond the worst case. We're going to allow expensive operations if they're balanced by cheap ones. This allows us the possibility of designing self-adjusting data structures that don't maintain a lot of structure but adapt to the way they're used. And in the max flow situation, what it amounts to is designing a self-adjusting kind of binary search. So that was the task that we ended up with, which we worked on while we were both at Bell Labs together. So let me remind you what a binary search tree is. This is much simpler than the linked cut trees I was talking about. This is just one piece of that. Here's a binary search tree. It's a data structure to store a set of items totally ordered so that search is efficient and we maintain the order. So here I've stored letters in alphabetical order, symmetric order. So everything in the left subtree of F, for example, is less than F. Everything in the right subtree of F is greater than F. If I want to search for P, I start at F. P is bigger, I go to M. P is bigger, I go to X. P is smaller, I find it. The best case of a binary search tree is a completely balanced tree in which all the nodes at the bottom, the leaves are on the bottom two levels, and the maximum path length is logarithmic, and then we get logarithmic search time. We can certainly achieve this if the data is given in advance, but what happens if we want to do insertions one after another? And what happens if we also want to do deletions? So here's a simple way to do insertion. We just follow the access path of the item. If we're going to fall off the tree at the bottom someplace because the item is not in the tree, we just plug it in there. So here's leaf insertion. If we want to insert R into our previous tree, the search path falls off the tree from the right pointer of P, and we just stick it in at the bottom here. Now, unfortunately, so if you insert items in uniformly random order into an empty binary search tree, you get a good tree, and there's been a lot of study of this, but you cannot assume uniform random behavior. And indeed, there are natural insertion sequences that produce the worst behavior. In particular, if you use this insertion algorithm and you insert items in increasing order, you get this tree. And now the worst case search time is linear, not logarithmic. The average search time is linear, not logarithmic. So to guarantee logarithmic access time and insertion time, you need to restructure the tree on every insertion. And the classic solution is to keep the tree somehow balanced, maintain some local balance condition that guarantees that all the paths are always logarithmic in length. You will know at least one. The first such balance condition was proposed by Addison, Belsky, and Landis, two Soviets in 1971. And there are many, many others, notably red-black trees, invented by Bayer in 1972 and made popular by a paper by Gibas and Cedric in 1978. In general, what we need here is a local balance condition and a way to restructure the tree after or during an update to maintain the balance. Here's an ABL tree. The balance condition is that the maximum path length going to the left is within 1 of the maximum path length going to the right. So we can store that information as a three-way state variable, which is either +1, -1, or 0 at each vertex. So +1 here means that it's deep to the right. That is, the maximum path length down the right side is 1 greater than down the left side. -1 means deep to the left, and 0, which the only examples are at the bottom here, means same maximum path length on both sides. Red-black trees, every node has one of two colors, red or black, so we only need 1 bit per node. The balance condition is that every red node has a black parent, and the number of black nodes on every path is exactly the same. And we treat nodes that are missing at the bottom as black. This kind of tree has also been called half-balanced because the maximum path length, the ratio of the maximum path length to the minimum path length is a notable factor of 2. In any case, there are many examples of balance conditions, and for all of these data structures, the way that restructuring works is to use rotations, which are local transformations that update the tree without changing the symmetric order. So to rotate at a node, a left child in this case means you replace its parent by it and push the parent down the other side. This takes constant time. We can restructure any tree to any other tree with the same set of items in the same order by doing sufficiently many rotations. And the way rebalancing works in these balanced tree structures is that when we do an insertion or deletion, that changes the balance. If we do an insertion, the path can get excessively long. If we do a deletion, it can get excessively short. And then we have to do rotations to fix things and update the balance information. And the only difference among these structures is in the details. In any case, we get guaranteed logarithmic, worst case, access, insertion, and deletion time. But at the cost of maintaining explicit balance, and at the cost of many cases, we rebalancing algorithms, and people have been known to get these wrong. But more importantly, often, access is not uniform. These data structures are specifically designed to minimize the worst case time for an operation. But what if we don't care about the worst case? We care about the total time, or maybe the access pattern is not uniform. What can we do? So that leads us to this idea of forget about maintaining some balance condition. Let's just somehow update the tree every time we do an access and insertion or deletion in a way that helps things later on, hopefully. This is like path compression. Path compression was a self-adjusting operation that improved things. And it was guaranteed to improve things because it only makes paths shorter. Now here it's more complicated because if we push things up, we're going to push other things down. So it's not clear this idea is going to work. But anyway, in an analogy with path compression, we might try something that when we access a key, we move it to the root via rotations. So it moves to the root, in the hope that we're going to access it again relatively soon, and then it's going to be cheap. So the straightforward way to do this, which is what we first tried, was just do rotations one at a time, moving the access item all the way to the root. But it's easy to produce a bad example. Indeed, if you start out with a bad tree and you access the items in sequential order, you never get to a well-balanced tree, and the total access time is quadratic for n accesses. So, and furthermore, you reproduce the original tree. And indeed, if you take any tree and you access the items in sequential order, you will end up with this bad tree, and then you get into this cycle again. So that doesn't work. Does one give up then? Well, we didn't give up. We tried the next idea, which is to do the rotations two at a time. This led us to what we call splay trees. The way this works is when we access an item, we'll move it to the root, but we'll do pairs of rotations. And the order in which we do the pairs of rotations depends upon the local situation. So there are actually 3 cases, or 6 if you pay attention to mirror image. So X is the node to be accessed. If it's 1 step away from the root, we just move it to the root by rotation, and then we're done. This would happen at the end. If we're at least 2 steps away from the root, and the 2 steps up alternate, we've got a right child and a left child, or symmetrically a left child and a right child, we do the rotations in bottom-up order. So we rotate X to the Y position, and then rotate X to the Z position, and the outcome looks like this. The zig-zig case, which is the bottom one here, is like weird case. If the next 2 steps up are in the same direction, left, left, or left, right, we do the top rotation first. We rotate Y up, and then we rotate X up. And this configuration turns into this. Now this one you might think is kind of balancing things. This one doesn't look like it's doing anything useful. But when you access an item, you do these steps until the item rises all the way to the top. And if you look at what happens in the long run, things start to get interesting. This is a artist's conception of a splay tree. This was drawn by George Stolfi for my Turing board lecture when I got the Turing board in 1986. It was a thrilling event. And if you look at this carefully, so it looks like these hands are doing rotations, but I just realized this a few years ago. it's not actually a good representation of how rotations work. I'll let you think about that. You can find this picture online easily. In any case, if you do, so here's an example of accessing a floor by splaying, and this is the pure zig-zag situation. So we want to access 4. We got a right followed by a left. 4 moves up in place of 5, and then 4 moves up again in place of 6, and 4 moves up in place of 7. And this is the picture at the end of the whole process. 4 is at the root. This access path has been cut into 2 paths. The nodes that are smaller than 4 and the nodes that are larger than 4. So everything on the access path has had its depth halved. And nobody has been pushed down by more than an additive constant amount. Here's the pure zig-zag case, which is kind of illustrates why zig-zag, even though locally it doesn't look so good, globally it's doing something interesting. We walk up this path, and what happens is the nodes on the path get paired up, so that this path gets split into the even nodes and the odd nodes. One set of nodes ends up on a path, and the other set of nodes get pushed slightly off the path. Again, everybody on the access path has moved up by essentially a factor of 2. Nobody gets pushed down by more than an additive constant, 2 or 3. So that's the empirical view of this thing. And it wouldn't be interesting except for the fact, at least to a theoretician, except that we were able to prove many interesting properties of this data structure. Through a long sequence of accesses, and we can include insertions and deletions, the time per access, insertion, or deletion is logarithmic. Now, this is in the amortized sense, summed over all the accesses. You can construct examples easily where the time for an individual access is linear. If you do a long sequence, it takes log time per access. Furthermore, if, for example, you have a situation where you're doing accesses and each item has a certain frequency of access, if you know this ahead of time, you could build a so-called optimum binary search tree that would minimize the average access cost. This data structure has the same performance within a constant factor, even though it doesn't know the access frequencies, doesn't use the access frequencies explicitly. And there are some other even more interesting situations in which you can prove that this data structure exploits time and space locality. So this led us to ask this question, just how good is this data structure? The audacious conjecture here is the dynamic optimality conjecture, which is that, in a sense, this is a universally optimal version of a binary search tree. What is the sense? I start out with some binary search tree. Let's forget about insertions and deletions, although we can include that. I want to do a sequence of accesses on this tree. You know the entire sequence of accesses. You know the initial tree. Every time you do an access, you pay the depth of the node that you want to access. Anytime you want, you can do a rotation. Cost 1 per rotation. Your cost for the sequence is the sum of the depths of the nodes at the time you do the accesses of them, plus the total number of rotations. Given any initial tree in any access sequence, there's some global optimum. The hypothesis or the conjecture is that no matter what initial tree, no matter what initial sequence, the total time for this simple online splitting algorithm is within a constant factor of the best possible algorithm for the given access sequence. This conjecture is now, almost 40 years old, maybe more than 40 years old. Nobody's proved it. It's still open. It's my favorite open problem in data structures. There's evidence to support it. Nobody's constructed a counterexample. For all you young people, It's a beautiful problem, but don't work on it exclusively, because nobody's solved it yet. Now, here's a reason to think that this is actually true. And this is a recent result of one of my PhD students from 2019, Caleb Levy. So we've got some access sequence. Suppose we delete some of the accesses, then the cost should go down, right? Certainly for the optimum algorithm, the cost cannot increase, because if I have an optimum algorithm for the total sequence and I drop out some accesses, I just run the algorithm for the total sequence, and that's an algorithm for the subsequence. So there's a monotonicity problem. Now, Splay does not have this monotonicity problem. Which is to say, you can construct examples where you drop out some accesses and the cost actually goes up. But it doesn't seem to go up by more than a constant factor. And if you could prove that with Splay, the cost never goes up by more than a constant factor, and you drop some accesses out of the sequence, you would have proved the dynamic optimality conjecture. And furthermore, this is if and only. So instead of thinking about comparing Splay to all possible offline algorithms, all you have to do is prove this property of Splay itself, or disprove it. That is, either prove that if you drop out some accesses, the cost only increases by a constant factor, or construct an example where this is not true, which would mean a family of examples for larger and larger constant factors. You can resolve this conjecture. Let me thank you for your time here. Let me just conclude with a few general remarks. My objective in research, here it is. The goal is to develop the best possible algorithms. So I like this notion that Paul Erdős promulgated. He had this idea of mathematical proofs from the book. That's the book in the sky. The best possible proof, elegant, simple. We'd like to design the same kind of algorithms. Algorithms as simple as possible with provable research bounds for important input classes and efficient in practice. The algorithms have to be simple or nobody's going to use them in practice. And I should say that the Splay trees, for example, they did get used in many places, in computer systems and other places. And we got the Paris Kanellakis Prize for theoretical work that had practical implications for this data structure. As computers get faster and memories get bigger, the design space expands. And it's useful to systematically explore the design space. Einstein may have said, make everything as simple as possible, but not simpler. In any case, it's a good principle. With that, thank you, and I'll be happy to take any questions you may have.
Thank you very much, Professor, for the inspiring talk. I hope we have plenty of questions. Please, the first one comes, first one gets a chance.
Do not be shy. Ask about anything.
Please. First one.
What was the innovation that changed your life?
The innovation that changed my life. I suppose the invention of the computer.
As simple as that. Oh, yeah.
Yeah, thank you, Robert, for your excellent talk. My question, can you describe the day when you found out that you were receiving the Turing Award? And my follow-up question, how did you sleep that night?
It was summertime. I was on vacation at the beach. I got a phone call. It was absolutely thrilling. but I slept very well that night, actually. These days a Turing Award is a big deal. When Hopcroft, so John Hopcroft, who I've worked with originally, and I got it together, it's now worth $1 million. When we got it, we split $1,000. It's the same Tiffany silver bowl, though. So actually, I'm very happy to have gotten it in the early days because I think it's much more competitive now, and I'm happy to ride in the reflected glory of the current winners. I'll change the question. The first award that I ever got that was incredible was when I got an undergraduate scholarship from the Los Angeles Times to go to college. I remember that when I was sitting in the bathtub, I got a telegram that my mother came into the bathroom with. That was really.
Thank you. More questions? Yes, coming up here.
Thank you for your talk. I had a question. What swayed you towards a PhD in computer science over a PhD in pure mathematics? And what were your research interests in mathematics at the time?
Well, I was at Caltech as an undergraduate, mostly interested in combinatorics. There were some very good combinatorialists at Caltech. So I was looking at four-color problem, not getting anywhere. I was looking at some versions of max flow. I wrote a little paper on some max flow problems. So I had done a lot of computer programming. It's very early days, but I had an opportunity in the summer to work at it was doing biostatistics. So I was doing computation on biostatistics, and I was fascinated by computers. And I figured that I could do mathematics that was applicable to algorithms, to computation, and so on. So when I applied to grad school, I applied both in math and in computer science. And I decided in favor of computer science. I guess I wanted to stay in California. Stanford seemed like a good place. But I could have gone into a math department. I think I would have done the same thing. I would have done theoretical CS, analysis of algorithms. I think it would not have changed my path. I wanted to do mathematics related to computation, discrete computation, not numerical analysis. Stuff like that. I was always fascinated by puzzles and games and so on. It's nice to see your ideas actually. The thing about computation as opposed to mathematical theorems, you can write a program and run it. It's a very concrete experience. So I hope that helps.
Thanks. So one more here, there, and there.
So before talking about spline trees, you mentioned red flag trees. So when looking at production level code, I noticed that red flag trees are way more common. I mean, previously this was the only type of slope balancing tree I know. And and my question would be, why are red flag trees so much more common than spline trees?
Well, I would say it's the question is if you want worst case behavior versus self-adjusting behavior. So the downside of sway trees is you're doing lots of rotations. So if you're in a situation where the axis pattern is reasonably uniform, the rotations are expensive, you're better off using the standard balanced tree. I would also say that people use the good enough solution. If you're writing production code, you don't experiment with a range of data structures. You just grab something off the shelf and plug it in. So there's plenty of room for improvement in computer systems by plugging in new algorithms, but the improvement may be incremental. So I don't know how we ever get some of these things into actual systems. The improvement has to be dramatic for people to be willing to change things.
Yeah, thank you. I'm actually curious about your last slide when you mentioned that it's interesting to develop simple algorithms and implementable algorithms, and in general, I'm interested in the direction of classical algorithms and data structures. As you know, like nowadays, there are some results like linear maximum flow or like some geometric data structures, modern structures are shaving off logarithmic factors. So I am curious about the direction of the algorithms in data structure. Like, do you think that current state is simplifying the existing results, or are there actual fundamental open problems that are still left to solve?
That's a couple of different questions. Yes, there is this tendency to complication, shall we say, at the expense of simplicity and maybe at the expense of practical running time. There are these beautiful, incredible results on max flow, min-cost flow, some results on shortest path algorithms and so on, that give asymptotically better bounds than what we had known. But if you put in the factors, you have let's compare square root with log squared, let us say. You go to 1 billion, I think log squared is bigger than square root of n. So you got to look at the asymptotics, actually. And there is a tendency in program committees to be to appreciate complexity for complexity's sake. That is my opinion. This is one reason why we've started a couple of conferences where the idea is to emphasize simplicity. There's the symposium on simple algorithms that we started in the United States, and now there's one in Europe too, which is part of ESA, I think. So I think there are some of us who believe in simplicity and are trying to promote it. I think there are beautiful ideas in these new algorithms, but it's going to take a while for people to distill out the useful practical stuff. I'm sure there are useful practical ideas in there, but not as presently constituted.
Dear Professor, thank you very much for your work and for the presentation and that you share your experience with us. I would like to ask you about how do you see the role of artificial intelligence now in such kind of research?
I think it's a very interesting open question, and I'm curious to see. My instruction to my students this semester, I tried to give problems in my algorithms class that are new so that they just can't look up the solution, which leads to interesting things like the problems are not always correct. There's some back and forth, that's another thing I try to point out is to students, you need to be skeptical about what you're reading. You need an active mind. So back to your question. So I told them they could use ChatGPT, for example, as long as they said they were using it, that they were explicit about it. I think we got one student who tried to use, that I know of, that tried to use ChatGPT to solve one of my problems and kind of failed. But I think these tools are going to be useful, and I don't know how, and I don't know by how much. I think it's a very interesting question. I think it's important that we use these things as tools, as enhancements to human ability, rather than as replacements for human beings. We need to trust but verify. I mean, these systems are subject to hallucinations and mistakes and so on and so forth. And this is not so good if you're relying on the artificial intelligence to fly your airplane or something. You would better verify the code. It's very early days. We really don't know. I don't have any better intuition than anybody else. They're optimists. I listened to a recent talk by Eric Schmidt, who thought that in 2 years these systems were going to be as good as the best professional research mathematician. I'm much more skeptical than that. So there's been this huge improvement, but we don't know how much farther it's going to go. I mean, the counter argument is, what are these systems good at? They absorb all the information that we have out there on the internet, right? And they're able to synthesize it. No human being has all this information at their disposal. But after that, what's next? Where does the creativity come from? There's some missing, I think there's still some missing component. There's some difference between the way people are intelligent and the way these systems work. I mean, I heard another interesting lecture about, do children have ideas? So children are inherently curious and experimenting and so on. They're motivated, they're emotional. These systems don't have any of this. So there's that component missing also. There are some missing pieces, so we need to be a little bit careful. That's my personal view of this.
So we have one more question here. Any other questions?
Okay, hi. So my favorite data structure is Cartesian tree or tree. So I was wondering what is basically the most fascinating data structure or algorithm that is not invented by you that you find basically everywhere else.
I think there's some beautiful hashing algorithms, like cookie hashing, for example, that are intriguing. Yes, that's the answer off the top of my head.
Next question. Was there?
Thank you for extremely interesting talk, and apologies for maybe a bit technical question, but this is related to the first problem you started to discuss, this quality problem, and frankly, it has some difficulties to dig up some real answers from random literature. So you presented this one algorithm for linear algorithm for quantity problem. Do you know what the situations with highest V surfaces? Are there any practical algorithms for torus or
people have certainly looked at that. I would have to go back myself and dig through to find out exactly what is known.
It was very strange. I found paper 15 years ago. People presented algorithm. 5 years later, paper there is error in this previous paper. So it's a bit
Thank you. Yeah, Gunter. So.
You have designed quite many data structures and algorithms, and I'm wondering which data structure is the most favorite for you and why?
But the ones that I've invented, or that I have?
Yes, your invented data structure.
Well, I like the compressed tree data structure, but I didn't invent it because of the fact that you get Ackermann function in the analysis is so strange. It's kind of amazing. And I like self-adjusting data structures. I like straight trees a lot.
Thanks. So, some more questions? Last chances. I will have one for myself. We saw a lot of these discoveries with one surname, two, maybe three. But we know in physics, biology, chemistry, engineering, there are many large, let's say, breakthroughs done by enormously huge groups of people. How do you see this changing in your field of computer science? Is there any drive towards larger groups, and yeah, how do you see this happening in the future?
So what I do is theoretical computer science, so we're proving theory, so it kind of requires a small group to talk to each other, although it's certainly true that I love collaboration, and I think there's more collaboration in theoretical computer science than in mathematics, for example, which is another reason I like being a computer scientist. I think group size is expanding over time. The recent work I did on Dijkstra's algorithm, that was for which we got the best paper award, that was 4 people, I think, and then we expanded it to 5 people. And I'm now working on another project that's 12 people, but I think that's actually too many. I think the ideal number is 3 or 4, maybe, because we need to communicate. I mean, different people bring different ideas to the table, but at some point, it's diminishing returns. If you're looking at an experimental project, even a systems project, it's easy to chop up the project into pieces and have each person do a different piece. Not so easy if you're trying to improve a theory. So I think it's always going to stay individuals or small groups. But I like the fact that we can work in small groups.
Thanks for the answer. So last chance, please. Anyone? If not, then please join me in thanking Professor Tarjan. It was a real pleasure to have you over here, and on behalf of the Department of Computer Science of the University of Latvia, and I think also on behalf of students and staff, we thank you for your time, for your insights, for your inspiration. And here's a small thank you from the Rector's office for your visit. Thank you a lot. Thanks.